Right now we're going to solve a particle kinematics problem. We've got a particle which is initially located at the origin, and the information we have here says that it moves along a straight line through a fluid such that its velocity is given by the equation shown. Our goal here is to determine the displacement of the particle during the first 3 seconds of its motion. Let's start by drawing a picture here to make sure that we can properly visualize what's going on. So let's see if we can draw a particle over here. Maybe somehow like that. And then we're told that it starts at the origin. So that suggests that we could define a coordinate system. And since we know that we have a straight line motion through a fluid medium, it makes sense to just go ahead and use the motion direction as one of the coordinate directions. So in order to visualize this, I'll put an x-axis over here, let's say. Maybe a y-axis up here. And I am going to visualize this particle moving here in the x direction. And it's going to move in a way where the velocity is given by an equation that looks like this. It's an exponential, and I'll point out here that this is given units of meters per second, but we're also defining our equation here in terms of time. So it's not a position coordinate, it's not like a function of x, it's a function of time here. So we're going to have to think a little bit about how to get at the information that we want to get to. Okay, so let's think about what an approach is going to be. So step one is something that we've actually already implicitly done, but it's a good habit to get into, and that is to consider the coordinate system. Okay. Now, the problem statement certainly suggested a coordinate system that makes sense, but in many cases you might have some more flexibility, and it's a good thing to insert this as step one in your approach. Now, the way this is going to work out is that we're really going to be able to express this as a position integral. So we know an equation for the velocity, and we know that position is somehow going to be some sort of integral of that equation. And the question is, what are the bounds of integration and how do we do the integral? Well, that's what we're going to do in step two. So we'll set up this position integral and make sure that we answer all of those questions in step two. Okay, so let's go ahead and do step one right here on this page. So step one is to define a coordinate system. So as I said, the problem statement clearly suggested a kind of coordinate system that we could use. We know that the velocity here is an explicit function of time, and that we're dealing with units of meters per second. Okay, so we sort of already completed this part. Again, any problem that you come up with, you might have more flexibility about how you define the coordinate system, so it's important to put step one in there so that you have a chance to reflect on what would be the most appropriate coordinate system for any given problem. Okay, that being said, let's go ahead and start step number two. So step two is to do a position integral. And perhaps the big question is, what is the form of that integral? What is it going to look like? So we're going to define a position coordinate in the x direction, and I'm going to call that coordinate s, and that's consistent with the notation in the book. And we know that s is related to v by a simple differential equation, so v is equal to the derivative of s with respect to t, and that means we can sort of separate that and we can write an equation which looks like this. So we've separated out the ds and the dt part, and what we're going to do here clearly is we're going to make these things into integrals, and that's going to be our position integral, as you shall see. Okay, so since our path seems clear now, we know that we can write an equation that looks like this. So ds, an integral, is going to be an integral of v dt, and that's going to look like this. So it's 1.8 1 minus e to the minus 0.3 t dt. Okay, so there is our equation that we were given. Now I've left the bounds of integration blank for the moment because we need to talk just a little bit about exactly how to do this. Okay, so the bounds of integration are going to look like this. In the problem statement, we are told that we're looking for t to be from 0 to 3. Okay, so we want to capture all of the motion across that time scale. And so what that means is that if we can express the left side of the equation above that, here, this ds, this will just be, that integral will just represent the change in position delta s. That's what we're looking for. And then if we want to integrate over t, now we know we're going to integrate over the interval 0 to 3. And so that is the way our integral is going to look. Okay, so now it's just a simple matter of going ahead and doing the integral and seeing what we get. So let's go ahead and do that. So we know that delta s now is going to be this integral from 0 to 3 of 1.8, 1 minus e to the minus 0.3 t dt, and we're going to be able to break this up in a couple of ways. So for example, here we're going to do 1.8 out in front, and then brackets we'll do an integral from 0 to 3 of 1 dt minus an integral from 0 to 3 of e to the minus 0.3 t dt, and we'll close that bracket. Now this first integral, you can see clearly this one is just going to be equal to 3. That's an easy one to do. Now the question is, what about this integral right here? There's a little bit of work to do there, and we're going to do that work on the next page. Let me stick with the red color here, and let's just focus on that one piece of the integral. So an integral from 0 to 3 of e to the minus 0.3 t dt. If you recall from your calculus class how to integrate this, we get this kind of an expression, 1 over minus 0.3 e to the minus 0.3 t, and we're going to evaluate that from 3 to 0. And so this then becomes minus 1 over 0.3 e to the minus 0.9, that's 0.3 times t is equal to 3, and then from that we're just going to subtract 1, and let me remind you that that 1, that's really just e to the 0. Okay, so if we do all that and we substitute it back into the original equation for delta s, we get delta s is equal to 1.8 times the bracket, it's 3 minus 1 over 0.3 times e to the minus 0.9 minus 1, there's the square bracket. And if we start doing the calculation, we can figure out that this term right here, this is about equal to 1.98. And so if we carry through the math to the next page, here's what we get. We get delta s is equal to 1.8, 3 minus 1.98, and this just ends up being delta s is equal to 1.84 meters, and that's from time equals 0 to time equals to 3 seconds. And there is your solution. Let's go ahead and review what we did. So the problem statement told us that we had a particle that was moving in a straight line according to a given equation. That equation was a function of time, and we were trying to figure out the displacement of that particle during the first 3 seconds of motion. So the first thing we did was consider a coordinate system, and in this case it was pretty straightforward to do. In the general case it might not be. You might have more flexibility with how you define the coordinate system. So here it just so happens that the first step was pretty straightforward. Step 2, however, defining the position integral, was a little bit more involved. The key here was the equation which related the velocity to the position coordinate s. But once we set out to do the integral, we could define the integral in terms of the velocity equation, go ahead and do the integral, and once we made our way through all the math, we ended up with the solution. Delta s is equal to 1.84 meters.